Hello ladies and gentlemen, my name is APugin from the Geological Survey of Canada. I'm presenting you shear and compressive wave data acquisition using multi-component vibrating source and land streamer. My co-authors are Barbara Dittiker, Kevin Brewer, and Timothy Cartwright. In the vicinity of Ottawa, Ontario, Canada, we have recorded many multi-component seismic datasets using an in-house multi-component vibrator source named microvibe and the land streamer. Receivers array with 48 3-component 28 Hz geophones are at 0.75 meter interval. We used 1, 2, 3 source and 3 receivers orientations, vertical V, inline horizontal H1, and transverse horizontal H2, and we identified several reflection wave modes in the field records. In this presentation, we present results from 3 surveys acquired in the vicinity of Ottawa. In this record, acquired with a shotgun source with vertical geophones, receivers at 1 meter, we show a seismic record with the expression of multiple wave modes. First, the PP compressive waves arriving early in the record, then the Biot slow P wave, rarely recognized but visible in this good quality record, followed by the low frequency surface wave. Then we can observe shear SS waves, hyperbolic reflections, and SP waves, conversion from shear to P wave. Various muting, filtering, and move-out correction tools are allowing us to process those wave phases separately. One of the sources we use at the survey is a 7-ton hydraulic vibrator driving a 140 kilogram mass from 20 to 300 Hz called the mini-vibe. Here the shaking occurs in a transverse H2 direction. This source is not well polarized, as despite the fact it shakes in horizontal mode, it also produces a considerable amount of compressive vertical energy. This is a 6-component seismic source developed at the survey using tactile transducers called the microvibe, providing signal from 5 to 800 Hz, shaking in vertical mode and horizontal mode H2. This source can also be rotated in any horizontal direction. The land streamer has also been designed at the survey using 28 Hz geophones in the 3 directions. The next slide will show you modeling and records that have been acquired with a sledgehammer with an H-beam in horizontal mode and a vertical hammer hit on a metal plate. Here we see a radiation pattern modeled using a P-wave velocity of 600 meters per second and an S-wave velocity of 150 meters per second. The radiation pattern of S-wave is at the vertical from the source within an angle of plus minus 30 degrees called SH. The corresponding field records show a good match with the model, with spectacular hyperbolic reflection on a vertical at the vertical of the shot record. With the vertical source, the radiation pattern shows a P compressive wave in green, radiating in all directions with shear hyperbolic reflection in higher angle called SV. The corresponding raw record show early P-wave events and later far offset S-wave seismic reflection. Here we show an end-on-shot record using a 12-gauge shotgun source. As in the previous slide, we can also see first the P-wave reflections and S-wave reflection at a higher angle. The horizontal H2 receiver record to the left shows S reflection at the vertical of the source that can be called SH. A converted P to S reflection is also visible in this record. This confirms our claim that a seismic source produces both P and S wave modes irrespective to the source type. Here is the shear SH wave filtered shot gather acquired with the microvibe in H2 transverse horizontal mode. You can notice a remarkable sequence of reflection. The processing requires a very accurate and thorough velocity analysis, as it is shown here to the right with this semblance analysis. This picking is not always easy when the geology is complex, in particular with data acquired over landslides. On the same location as in the shear wave record from the previous slide, here is a raw P wave record acquired in vertical mode. Based on my experience, the P-wave has been always easier to pick in a semblance analysis as the error margin is larger. But here, for example, one has to use his own experience to not pick those near-surface multiple instead of picking direct P-waves or reflection energy. This slide shows an SH reflection seismic section acquired with a microvibe source and receivers in H2 transverse mode, where the main strong bedrock reflection is at approximately 25 meter depth to the left of the section. This section shows a remarkable resolution, as much as less than 1 meter in the sediment covering those gravel and diamicton mounds. This section below can be compared with an SV section acquired with the microvibe source and receivers in V vertical mode. The features appear very similar, but with a slightly lesser resolution and a different signal wave shape. Now here we are comparing the same SH wave section with the PP wave section here below. Here you can see that the wavelengths of the shear wave signal is amazingly much shorter than the wavelengths in the PP wave section, with a velocity ratio S to P, which is approximately 1:8. Note also the ultra-shallow reflection that are visible in the S-wave section. The velocity analysis allows us to plot a depth section highlighting various interval velocity units. These types of velocity plots are what usually civil engineers need for the planning of construction, tunnel digging, or to test levees and earth dam construction. This then allows a geologist to interpret this section. The lower unit is a hard limestone bedrock that is here not penetrated by shear wave, as there is too high velocity contrast between the top sediment and the rock. The mounds are filled with gravel and diamicton as confirmed with borehole data, and this is a reservoir with an artesian aquifer. Highlighted in yellow, a sand layer is present just over bedrock, and 2 units of clay separated by an erosion surface is picked in mauve color. In this slide, we show an example of a 6 components, 500 meters long section using the microvibe. The top 3 sections are the 3 component sections processed from the data acquired with the source shaking vertically, and the lower 3 plots are the process section using the source in horizontal transverse mode H2. Every section displays some reflection energy at various time and various amplitude. However, 2 outstanding sections are distinguishing themselves from the other sections. This is first the VV vertical source and receivers sections in the shallow part, and then the H2 section in the deeper part of the section. Knowing the fact that shear wave is more vertically polarized in the shallow part and horizontally polarized in the deeper part, we have combined those 2 SV and SH sections to form and get the best of this 6 component section. As a follow-up from the previous slide, we have acquired a mini-vibe 3.8 kilometer long section on the same line, and we use this heavy vibe with its shaking mass in inline H1 direction. As in the previous slide, we also have combined the SV vertical shear and the SH horizontal shear, and we could process that exceptional shear wave section. I remind you that the mini-vibe, even in horizontal mode, it also generates a considerable amount of vertical shaking. We have computed a 2D polarization analysis between the vertical V component and the horizontal H1. In white, we can see that the vertical polarization mostly occurs in the first 300-400 milliseconds, and the deeper sediments are more horizontally polarized in darker gray and very horizontal polarized in black, as the high reflection amplitude are corresponding to the sediment bedrock interface. This is a new approach for understanding shear wave data polarization that could be pursued with even more research. This shear wave section has been shifted on a datum using the surface topography, and we can compare it with a P-wave section extracted from the same data set using the vertical receiver component only. Here again, we can see how much better resolution we can get with shear wave data. This section has then been converted in depths and then interpreted for locating an appropriate spot for drilling a borehole. Based on our seismic facies analysis, we predicted that an aquifer would be met at a depth of 95 meters. The borehole drilling was stopped at a depth of 93.5 meters as some water was starting to flow up the well, and the drilling equipment was not set for handling an artesian high-pressure flow. The top of bedrock interface show a deep basin and a gorge to the left. High reflectivity gravel with stratified sand can be interpreted in the section, then followed by the first horizontally polarized marine clay 1 and the vertically polarized clay 2. We don't know if this is a coincidence, but there is a significant difference between the two clays, and the clay 1 has much higher content of carbonate, as the clay 2 has a higher content of silica minerals. In conclusion, despite the fact that any source type can generate any combination of wave modes, PP, PS, SP, and SS, partitioning of the source energy depends on the source orientation with VP-VS ratio. Our examples demonstrate that the most prominent PP reflection energy is recorded with the VV source receiver orientation, whereas the most prominent SS reflection energy is preferentially recorded by the horizontal source receiver orientation, H2H2, or depending on the type of source used, with possibility to obtain polarized shear wave near surface data in all other vibrating and receiving directions. Thank you for your attention.